started talking about this yesterday, and we made it just to number 2, where we started to talk about the list of the possible forces that could be acting on an object. Today, we got to get through all the way through. But I want to tell you something before we get started. This does not solve a problem. You will have homework questions, sure. But this is what Newton's laws are designed to do. They are designed to allow you to analyze a situation. You might be able to solve a problem from this, but this is what an engineer would do to try and analyze the situation that he's been placed in. So we're doing the work. At the end, you're going to generate a unique relationship that matches just the problem you've been given. So this creates something by the time we're done. What it creates may be used to be able to solve your problem. So I want you to be clear. This is the model, but what we produce isn't the answer to your problem. It produces a group of equations that may or may not be able to solve your problem. I'm going to give you guys all of the information you need to be able to make the decisions on a free body diagram. You're the one who has to apply the rules. I would strongly encourage you to take detailed notes. We're going to start with a single situation, and it's a very simple situation. I was going to try and do it yesterday, but we didn't have enough time. So the situation is the book on the table. We're going to do a bunch of examples across the course of today. I'm hoping 4, and we'll probably get to a total of 10. But our first example is the book on the table. So what I mean by that is I want to use the force concept model to analyze what's happening to the book as it rests on the table. So I'm going to take a moment and draw a quick picture of the book on the table. This is because I want you to have in your notes a kind of quick representation of what it is we were talking about in the class. Because otherwise, all your notes are going to have is what I say and write on the board. And this way, if you're at least writing down all the things I put on the board, this will be one of them, right? So this is the book as it rests on the table. Your first job, and the first thing on the list, is to decide whether this is a first law problem or a second law problem. Yesterday when we talked about this, we indicated that first law problems are either stationary or traveling at a constant velocity. And we indicated that that would force us to use Newton's first law. Whereas second law problems are ones where the object is accelerating. This is also the default choice if you don't know. In fact, if they tell you about the forces, you may have to be figuring out whether they're in balance or not. You would assume unbalanced unless shown to be balanced. Now we're focusing on first law problems for our first couple of days. So these are going to be first law situations. We'll come back to Newton's second law when we get good at doing this initial stuff. After we decided this is a first law problem or a second law problem, our next job is to draw a free body diagram. So in drawing a free body diagram, I gave you a series of steps yesterday about the different forces. What I want to do today is kind of talk to you a little bit about what I expect to see in a free body diagram. The first thing is each object gets its own diagram. If it has mass. And is a part of the problem. That's kind of an esoteric sentence. I know I'm writing fast, but I'm in a hurry. I want to get to the good stuff. Each object gets its own diagram if it has mass and it's a part of the problem. The table is not a part of the problem, so I'm not going to draw a diagram for the table. I'm just drawing a diagram for the book. Does that make sense? It's the problem. I asked about the book. But there will be problems where they will explicitly state that something is massless. So 2 boxes are hung by a massless string across a massless pulley. They are telling you when they say that to ignore those objects. There are no massless strings and massless pulleys. It's a construct for you to be able to do a physics problem. But oftentimes, you'll get very good results, even if you ignore the mass of the pulley and the mass of the string. because often the string has very little mass compared to the other stuff, and therefore it doesn't really affect the outcome. Now, there are problems where you can't take them and ignore them, where they will say it's a massive pulley, or they will say the string has a mass and it's affecting the problem. Under those circumstances, they all get their own diagram. Does that make sense? All right. Now, the next thing is, a free body diagram is just a collection of arrows. We draw arrows from a dot that represents the center of mass. So we reduce each object to a dot, and we draw arrows representing forces. A dot that represents the center of the mass. The arrows represent forces, sorry. Getting way ahead of myself. The arrows should be drawn to scale. So when you're drawing a free body diagram, every object is represented in its own diagram. Every object is reduced to a dot, and then you draw arrows from the dot that represent each of the forces acting on the object. The arrows need to be drawn to scale, meaning if you're told that one force is half the size of the other, then by gosh, make one of them half the size of the other. You have a ruler. You should be using it. Any questions? Anything on your phone that's interesting? Mostly, I don't like grading quizzes where they're blank and then hearing from the counselor about how people can't do stuff in my class, which I had to hear about this week. So let me get this out of the way. Get that out of the way. And let's talk about what happens when you're drawing a free body diagram. A free body diagram is a collection of the forces acting on the object. So once you've got your dot in place, you're going to go through and ask yourself a series of questions about which forces you believe are in action on your object. They're in three categories: the fundamental forces, we talked about those yesterday. I gave you three of them, gave them in order from weakest to strongest and from longest range to shortest range. For this class though, that's just gravity, which we're going to call weight. I need you to know those three forces. I need you to know them in order. I need you to be able to recognize them on a multiple choice test. You got it? That's the extent of what you need to know. But in this class, when we're dealing with forces, the only force that shows up is the gravitational force. There are many forces with which we don't have an expression for them, but weight is kind of unique in that there is an expression to describe weight. Weight is the product of the mass and the acceleration of gravity. So we'll all say that weight is mg. So to draw this force, and when I ask you guys in class, are there any conservative forces acting on the object, be the first person to say yes, and draw an arrow downwards. Every object we're going to see in this classroom is going to be experiencing the gravitational force. So you know it will be acting on your objects. So you draw it, draw an arrow downwards, and then provide it with a label. A force without a label will not count. All right. Sometimes, and it's okay, you'll see me just write mg. Especially if there's multiple objects, I'll probably write m1g, m2g, m3g. That way I can separate them out. Once you're done with the conservative forces, you move on to the next force, which is going to be the contact forces. We only talked about two of them, but there are lots of contact forces. The ones I want you to know right now are normal forces and tension forces. I'll use a capital N for normal and a capital T for tension. Normal forces are pushing forces. And they're called normal not because they are ordinary. They're called normal using the geometry word for perpendicular. They are normal to the surface. I'm not going to write all that, but you should. Normal forces are always perpendicular to the surface. So I'll draw the little perpendicular symbol there, so you'll write something down. But I would write in there that if you believe an object is in contact with a surface, then it is experiencing a normal force, and you will have to draw an arrow perpendicular to the surface. An object can be experiencing more than one normal force because it can be in contact with more than one surface at once. You could have it resting on the table and me resting my hand on top of it. You'll be having a normal force from the table and a normal force from my hand. So you need to be careful. Every surface in contact with an object provides a force. The moment two things touch, there's a force between them. Now, in dealing with this problem, there's clearly a normal force. The book's in contact with the table. The normal force must be perpendicular to the table. So that's got to be upwards. Tension forces require some kind of conduit. They're pulling forces. So you're looking for a string, or a rope, or a cord, or something. An object can be experiencing lots of tension forces, one for every string acting on it. Tension forces, though, act in the direction of the string. So whatever direction the string is attached, that's the direction it's acting. So tension forces can really be in almost any direction. There are other contact forces, and we'll see some later today, but right now that's a good start. After this, there are resistive forces. Now, there are plenty of resistive forces, but this class will only focus on two: friction and air resistance. I will use a lowercase f for friction and usually an uppercase D for air resistance, drag. Friction is a force that attempts to prevent one surface from sliding past another. Friction is a force that attempts to prevent one surface from sliding past another. Should I go 3 times on that? Friction is a force that attempts to prevent one surface from sliding past another. There's 2 kinds of frictional forces. There's sliding friction, where the surfaces are moving with respect to each other. But there's also static friction, friction that holds 2 objects in place. Regardless of which type you may have, one's attached to motion and one's attached to objects that are stationary. But friction is opposing motion. So it's trying to prevent one surface from sliding past another. Now there's subtext here, and if you're able to read subtext, you should already have made a pronouncement on this. That friction has to be parallel to the surface. It has to be. In fact, as a rule, friction will be parallel to the surface. So by definition, it's perpendicular to the normal force. Right? If the normal force is perpendicular to the surface and friction is parallel to the surface, the normal force must be perpendicular to the frictional force. Everybody understand what I'm saying? I'd write it down. In addition to that, there is no friction without a normal force. Normal forces occur when surfaces are in contact. If there's no surface in contact, there's no friction, because friction is a force between surfaces. So normal force is required for friction. Friction occurs when there's a normal force. However, do we believe there's a frictional force acting on the book? Is one required to keep the book in place? I think the surface is level. Do you think it's level? If you were to draw friction, what direction would you draw it? Because anything I add to this diagram would be unbalanced, right? So I don't think there's a frictional force in this example, because there's nothing required to keep the book on the table. The book is level. The table is level. So I think we're done. I think we've dealt with all the forces that are acting on our system. Any question about this list? All right. We shall see. Apply a coordinate system and resolve off-axis forces. Now, applying a coordinate system means you're placing X and Y over the top of your free body diagram. Now, truthfully, at this moment, we are done with the free body diagram. If you were asked to turn one in for a test, this is what you would do. In fact, on a test, it may say, do not add anything to your free body diagram. If you do, draw a separate diagram to do your work on. So what we're doing now is leaving the free body diagram and beginning the work necessary to use it to solve a problem. Okay? I will be clear on a test where you have to stop and where you have to change if you're going to do something else. But if you need to do work on your diagram, you do it separate. So resolving forces and all that happens someplace else. There are two priorities here. You can draw your coordinate system any way you want, but if you want to have a chance at solving the problem, follow these priorities. Priority number one is to align a positive direction, X or Y or Z, with the direction of the acceleration. Your first priority is to align a positive direction with the direction of the acceleration. Doesn't matter if it's X or Y. If you can't do that, or if your object's not accelerating, then your next priority is to align the coordinate system with as many forces as possible. Now, this one is kind of a silly example of this, but I have students who will do crazy stuff. Look, I can put X in any direction I want, but understand that whatever direction you choose for X, you are assigning a direction for Y. You can't just decide now to put Y this direction if X is at an angle. You understand that X and Y have to be perpendicular to each other. Every year I see people do this. And every year, I get very, very sad. So, if you're making your X direction this way, your Y direction has to be perpendicular to it. So, this system isn't accelerating. And because this system isn't accelerating, I can align my coordinate system in such a way as to be aligned with as many forces as possible. It would make the most sense then to align it like that. That way my Y direction is aligned with both forces. You can choose any direction I want, but this is aligned with as many forces as possible. All right, we've applied a coordinate system. If there were any off-axis components, like a force in this direction, it would be at this time that we would have to resolve that into components. Break it up into its X component and its Y component. But we don't have any off-axis components. So we can move on to the next step. We'll do these at the same time. Apply Newton's law in each dimension and create functions to solve the problem. This is a Newton's first law problem. Sum of the forces in the X direction equals 0. Sum of the forces in the Y direction equals 0. Let's talk about what this actually means so you understand fully what I'm expecting. This is not an equation. In fact, this is not a function of any kind. This is an instruction. It's telling you specifically what to do. It's saying to add up all of the forces in a particular direction. That little bar there means taking into account the direction. That means positive or negative. And setting them equal to 0. That's the directions. Add up all of the forces in a particular direction, taking into account the direction, and set them equal to 0. So, there are no forces in the x direction. I don't have to do anything there. There are 2 forces in the y direction. So, the normal force is upwards, I will make it positive. I will add it to the weight, which is downwards. I'll make that negative. And I will set that equal to 0. Add up all the forces in a particular direction, taking into account their direction, and set them equal to 0. All that work to say n minus w equals 0. Now, this was a bit of a ridiculous example. And I'm not sure what this tells us, except that the normal force must equal the weight of the book. That's all it really does tell us. But again, all the force concept model was ever going to tell us was the size of an individual force or the size of an acceleration. That was all it was going to tell us. This analysis leads us to a couple of created functions that fit this problem. That's what the force concept model does. All right, example number 2. Can I borrow somebody's calculator? Does that match the scenario pretty good? Remember, the calculator is what we're interested in. So I want a free body diagram that tells me about the forces acting on the calculator. So to start off, I'm going to draw a free body diagram. There's one object. Because there's one object, I will draw a single dot to represent the center of mass of that object. Then, sometimes you're given a force that you must use in your problem. A kid pushes on the box. A train pulls on the train cars. A child pulls on a wagon. You might just be given a force that you must use. Oftentimes we'll just call this an applied force. It's usually a contact force of some sort. Whatever it is, just add it to your set of forces and usually evaluate it when you're evaluating the contact forces. I'll draw a picture. That's what I'm fantastic at pictures, a true artist. Book. Some guy applying a force. And because of that force, the book moved up the wall at a constant velocity. The book is the object. I want to say it again, though. Sometimes you're just given a force that you have to use. And often you're given a force and the angle. So just call it the applied force. But let's not make this mistake. On a free body diagram, all forces are drawn so that they are at the center of the object, drawn outwards. So don't ever draw the arrow towards the object. It might be drawn this way in the picture. It might sound like this in the discussion of the problem. But when you draw your free body diagram, all forces start at the dot and are drawn away from the dot. All right? So I'll help you out. I drew a dot. Is there any conservative force acting on the book? Yes. So did you draw an arrow to represent the weight of the book? This should be the easy one. So an arrow downwards. A force was given to you that you had to use. Hard to screw that one up. Right? I even put a big picture, the big bold arrow on the board. So I hope that you didn't see. I wasn't trying to trick you. There should be a force directed at an angle. And consider how long this one should be. Based on that angle, it has to at least lift the weight of the book. So, it might be pretty long. Don't assume that this is the length of the arrow. Is the book in contact with a surface? So there must be a force acting on the book that is perpendicular to the surface in contact. Saw a lot of problems with this one out there. At least 6. But the normal force has to be this way. It's not going to be into the wall. The wall is pushing outwards to prevent the book from going through the wall. I mean, I know I'm huge. Maybe I could push the book through the wall. But apparently not this time. The wall prevented the book from going through. So the normal force should be away from the wall to try and prevent the book from going through it. Now, I saw some weird stuff here, too. What direction was the book sliding? Was it up or down? Friction is a force that attempts to oppose the motion of the object, right? It prevents one surface from sliding past the other. So I would expect that friction was acting downwards because the book was moving upwards. Friction is trying to prevent this motion of the book. So I think the only choices were up and down because it had to be perpendicular to the normal force. But I did have at least 1 or 2 people who had friction this way. Yay! That's wrong. You understand? Taking the test again. Now, something to keep in mind, you can stack forces if they're in one direction. You can draw them stacked, or you can draw them side by side. I generally draw them side by side, but drawing them stacked is just fine. So whatever helps you understand this best, do that. I need to draw a coordinate system here. And since it's moving at constant velocity and not accelerating, I can choose the second priority, which is to draw it in such a way as to match up with all the forces, or as many forces as possible. That would not be a coordinate system lined up with this force. I think that's the wrong way to go, don't you? So I would probably draw it so that it's lined up with this set of forces, because that would mean that the next one is this way. So this would be the X direction, this would be the Y direction. Now, this angle is this angle, because I know geometry. Those are vertical angles. You need to find that kind of stuff out. But that also means that there's going to be FA in the Y direction and FA in the X direction. And I bet those two are related to sine and cosine. I'm thinking this is the opposite side. I'm thinking this is the adjacent side, right? You guys are remembering this stuff. This is why we learned all that trig. Probably something like, FAX equals FA sine theta. And FAY is going to be FA cosine theta. Because I know trig. I can do my trig fast. You're going to need to do your trig fast. But I'm also going to say that net force in the X direction equals 0. That's Newton's first law. This is a first law problem. And I'm thinking I've got FA in the X direction minus normal force equals 0. Right? I'm applying Newton's laws, which says add up all the forces, taking into account their direction, and set them equal to 0. Any question about that choice? Net force in the Y direction will also equal 0. And I have FAY minus friction minus weight equals 0. I have created 2 custom relationships that fit just this problem. Again, if you're just writing that stuff down, give yourself context. Why are we doing this? Which step are we on? That way your notes will have meaning for you later. We're on the last two steps, applying a coordinate system, breaking our off-axis vectors into components, and then applying Newton's laws. They will generate a relationship. All right, example number 4. We have just enough time to get it out there. Mr. Shelton owns a business at the strip mall where Mr. Shelton's business is. He has his door on the sidewalk. That's a doorknob. He would like people to know about his business, so he's going to hang a sign above his door so people walking along the strip mall can see his business. He decides to hang that sign using a cable. 2 cables, actually. One that's horizontal and one that's at an angle. Draw a free body diagram so we could figure out how strong the cables would have to be. Three arrows. This is what you guys got? 3 arrows? Something like that? Be careful. I didn't draw this particularly well to scale. I'm pretty sure this is going to have to be a pretty long vector because it has to both lift this object and make sure it balances that force. All right, folks. I will be posting